I hope you're able to hear me. Okay, good afternoon and welcome to this session. And I'm Raghu. I'm from the Indian Institute of Technology in Chennai, Madras, in Tamil Nadu, in southern part of India. This is the work done by my master's student who is working on the riveted joints. And we have taken one case study where we are looking at this, the lozenge pattern, the 3-to-1 lozenge pattern for riveted joints, which are subjected to kind of a biaxial loading condition. So the crack path is predicted by using the maximum energy release rate criteria for this purpose. So this is the outline of my presentation. So intro and then characterization, propagation, and variables that affect literature review, aim of the study. Then the SIF predictions and validation, results and discussions. So as you know, riveted joints are used in various domains, which is aerospace, transportation, construction, shipbuilding. Because today we are now moving away from these riveted joints in terms of aerospace, engineering, but we still find that some of them use the construction of the civil and as well as on the other domains that we use them. And one of the problems that you look at it is it's actually a stress concentrator. The classical theories of riveted joints says that it's a stress concentrator, but very often we consider that it's an unfilled hole, and as a consequence we think that Kg is as factor of 3 in a circular hole in an infinite plane. But the moment you transfer the force through a kind of a rivet or through a pin, you're going to end up having a completely different stress scenario. And this is what makes the difference between an unfilled, the stress concentrator and the filled stress concentrator. So if you look at this case, you have a joint where you are transferring the force from one end A of this component to the other end B. So you have a number of rivets. So there is a kind of, the study which suggests from Skyway, which says that, your rivets in A is more critical than B. And there are other kinds of joints that have been done. In fact, in the aerospace domain, a lot of studies have been done in terms of the multiple site damage and the widespread fatigue damage that goes on, especially when you have these kind of rivets. What is important for you to note is that, to alleviate some of these early fractures, what we have done is some kind of a interference fit to these holes. That means we put an oversized rivet or an oversized plug inside that to allow for the kind of the residual compressive stresses to be developed. The other option is you can insert a bush, and then you can also do the similar thing. So we have kind of worked on many of these things. So the variables that affect the stress intensity factor, in the case that there is a crack that initiates, because all of us remember the early failure studies where we are looking at this, the airlines or this common airplane accidents, this pressurizing, depressurizing, riveted joints, they were all the classical stuff. So you notice that there are a number of variables that actually affect the stress intensity factor of the riveted joints. In the unlikely event that there is a crack, you will notice that it will be influenced by the geometry in terms of the size of this riveted hole size and the number of holes. Then what is the pitch, whether you have used any kind of a stiffener or whether you have done some kind of step drilling. All this kind of stuff is there. In fact, today people look in terms of an additional hole to be provided before a stress concentrator, so that you can make this stress flow lines to be more streamlined. As a consequence, you can alleviate the severity of the crack in those locations. Of course, loading, you have uniaxial, biaxial, then you have this torsional loads. Sometimes you have this constant amplitude, variable amplitude, and so on. And in terms of the crack, you will notice that it can be a through crack, part through cracks. So much of literature talks about all these things. Then today we look at it in terms of the residual stress and also the environmental effect, and then on the crack size. So a number of these variables. But when you look at the load transfer mechanism from the literature, you will notice that there are simple methods like use of a point force. In other case, you try to assume that it's a uniform bearing load. But then, we have learned that it is not a uniform bearing load. You will find that there is a kind of a cosine distribution, or you may find that there is a Gilchrist distribution of the kind of force, and as a consequence, it affects your kind of life prediction or the stress intensity factor prediction at these joints, depending on whether you are having a snap fit or whether you are having a kind of an interference fit or a clearance fit. These things will affect. So, as part of our larger study, I mean, we have a larger plan where we realize that in a riveted joint, it is not possible for you to get a perfect fit. You may find sometimes the interference fit, and after some time usage, like what we have been talking about in the previous talks, due to fretting and the wear that will take place, it can become loosened. And after that, the force transfer mechanism can be different. It can affect your stress intensity factor. So that's the idea that we are looking at. So sometimes, that's what I told you, we also look at the step drilled holes over here, which will actually kind of reduce the velocity of the crack in all these cases. And we had one of the students who worked on the effect of the cold working on these joints, and we figured out how it kind of affects the stress intensity function as a function of the crack length for different conditions. So you can see here for an aluminum alloy 2024 T3, you will notice that there is different case studies that have been done depending on the cold work, no cold work, or the cold work in one case and the higher cold work. You will notice that the stress intensity factor will kind of tend to be influenced by the cold work. So there is improvement in terms of the the life because of the stress intensity factor being reduced due to this cold working. So that is what you notice over here. Then we also had a study by one of my students where we looked at a crack that is there in this finite width plate geometry with a central fold with a rivet that is there with the diameter of 8 millimeter rivet. And then we kind of studied what happens to the stress intensity factor as you change your interference fit levels. So it can be anywhere from snug fit, which is 0.0 percentage of interference, and it can go up to about 0.5%. We realize that there is a optimum kind of interference which will allow you to get the maximum the benefits due to the interference fit, because beyond that you will notice that it does not make a difference in these cases. So which is what has been shown over here. If you have a effect of interference plus there is a hole that is attached above the kind of this stress concentrator. Of course, due to symmetry, we'll also place one more step over here. Then you will notice that it can kind of give you a better effect in terms of the reducing the severity of the hole or the rivet hole in these cases. So in fact, 8 mm additional hole and a 0.3% interference gives you a maximum kind of a reduction in interference rate. So we then took to the case where there is a lozenge pattern. So typically this is what is called as a lozenge pattern, where you have a 1, 2, 3, and you could go for a higher levels, maybe from 3 next you can keep even 5, but typically people look at this 1, 2, 3 as the joint that is being considered for many of the constructions. And now these are places where there is a stress concentration. So if you imagine you are applying a stress in this direction and then reacted by the other direction, you will notice that there is a force flow or the stress flow that is taking place under these configurations. What we understood was that this fold is the most critical of all these cases. And as a consequence, if there is a crack that is initiating from this configuration, you will notice that it can influence the kind of the strength of this joint itself. So in this case, we have considered a optimum interference level of about 0.1% to 0.15%, which has been the best option that is available. But for the purpose of understanding what is the effect in terms of the crack, because even though I say that these all have to be kind of identically manufactured riveted joints, in practice you will never find them to be possible. You will find that there could be some where there is interference, there could be some where there is clearance that is taking place, because engineering is all about tolerances. You will notice that there could be a crack that is initiating any one of these holes for this matter. So now we also want to study what happens if there is a crack that is initiating in one of these joints or in some other joint where it has a pliability to quickly kind of merge to form a larger crack. So this is what we had done before. But one of the, the points to be noted is that we allowed this, the crack to be always plane perpendicular to the direction of the loading, which was a kind of a, initial and a simplistic assumption that was done. But we wanted to modify that to see what is the actual crack direction and how it varies in terms of the crack driving force. So the aim of this particular study is to employ the maximum principal stress direction for crack initiation, and then do the crack advance based on the maximum energy release rate criteria. So today you notice the last 1.5 decades, people are talking more in terms of the crack direction to be determined by using the maximum energy release rate. So which is what we wanted to do, especially if you are looking at a thicker plate or a thicker geometry where there could be a 3-dimensional crack growth. You can force or you can expect that the crack will not be always plane perpendicular. It can be in some angle, and the kink angle can mean that it's a mixed mode, the cracking, and that's what we would be able to identify by going through this. So the variation of SIF on the crack length in the is 3:1 lozenge pattern, and we chose for this study what is called as a biaxial loading condition. So many of these studies assume that as it is a uniaxial joint, but if you have a pattern like what I showed in the beginning, where there is a bridge girder or something like that, where you are putting a riveted joint, you might find that there is a biaxial loading condition. So we need to identify what is the crack driving force over there. So the most critical hole, and then what is the effect of biaxiality, and if there is any kind of crack shadowing that will take place. These are the things that what we wanted to study. So just to give you a feel for what is the difference between looking at the plane perpendicular crack path and then what you can predict by using the maximum energy release rate, you will notice that the blue and the red lines, what you see, they give you a feel for what is the maximum energy release rate based crack path, whereas what you see as a plane perpendicular as a black line is the one that is seen for the the maximum principal stress direction, that what you allow the crack to grow. So we have now nomenclatured it by saying that this is a row 1, row 2, and row 3, and then row 1 has one riveted joint, and then row 2 and 3 have got 2 and 3 kind of rivets over there. So in this case, you will notice that the SIF with the crack length was identified by going through this exercise, and the chart shows that the beta function, that is actually the kind of the crack driving force function, which is a function of the crack length 2A by W. You will notice that if you are looking at H1, which is the plane perpendicular hole 1, then you will notice that based on the plane perpendicularity, you will estimate a crack length, crack driving force to be like this. But if you are looking at what is called as the yellow line over here, you will notice that it is based on the maximum energy release rate criteria. So this is also shown over here in terms of SIF variation, in terms of the plane perpendicular crack front as a function of these two holes, hole 1 and the hole 2 in these cases. Okay, so now we look at this, the biaxial loading configuration. So typically in the literature, you will notice that people work with this cruciform specimen, but the only difference is most of them use some kind of a crack which is introduced into the center of this sample at some angle, and then they want to study how the crack is going to grow. But we use that as a benchmark to validate our FEM, and then later on we removed this crack and then took this as a joint which has a kind of a susceptibility to failure at these riveted points, and then looked at what is the effect of crack driving force in these cases. I mean, it may be kind of silly to make this observation because nobody introduces a crack in these geometries to kind of identify what is the crack driving force, because when we start a sample or a material or a geometric design, we always assume it's a flaw free, and then we don't know where it will initiate. So that's where we are looking at it. Now we also have these crack tip designations. The one which is at the if you look at any of this, what is at the top is crack tip 1 and bottom is at the crack tip 2. That's what is being explained over here. So we did this for a steel plate which has a elastic constant, as what is shown over here. There's a linear elastic analysis that has been done. And the 2D plane stress linear elastic fracture mechanics analysis was kind of done on this. A seam crack, as what is being described by the Abacus, the software has been used to model this. And basically, a seam is nothing but an edge for a 2D or a face for a 3D analysis with the overlapping nodes. So you can see here the kind of a seam crack that is displayed. And at the time of analysis, these nodes are separated from each other, and then the solver treats this as a kind of a crack. So this is the flow chart of what we do for the purpose of identifying the stress intensity factor in this case. So uncracked model with the necessary boundary conditions, determining what is the maximum principal stress direction, generate the initial seam crack in maximum principal stress direction, and calculate the SAF and the maximum energy in the straight direction. And then you can give a crack increment in the NERR direction. Technically, if you know what is the DU that you are generating by this process, it is possible for us to also find out what is the DA to be done. But for the purpose of simplicity, we have taken this arbitrary crack increment of 1 millimeter along the NERR direction, and we can always refine our kind of calculations by going through this DU and the DA relationship. So calculate the SAF, and then if the crack size reaches the desired value, then you can quit. Otherwise, you continue this kind of a routine. So in-plane biaxial loading was applied in the X and Y directions of the pins. So you could do an equibiaxial loading. So you can have sigma Y and sigma X to be equal, or you can also consider the variability in terms of sigma Y and sigma X. So we have done some variability in sigma Y and sigma X. So as what you can see over here, 3 different load ratios of 0.25, 0.5, 0.75 was done, in addition to considering that one as a reference. So the displacement along the y-axis was fixed for the left and right side pins, and then the displacement along x-axis was fixed for the top and bottom side pins. And representative stress of 60 MPa was applied, and load is equally shared with the event location, and we calculated what is the effective SAF in this case. So this shows the comparison that what we did with the literature model, where there was a crack that was initiated, and then this shows a good comparison between the kind of the model and then the mesh the results and what we have found in this case. So the finite element used the mesh size of about 20 microns, and then CTS8 was the the element that was used for this, and we also looked at what is the kind of the mesh convergence for all these cases. So now if you look at this, this shows the kind of the joint in this location where we have identified 1, 3, 5, and 4. So at each of these locations, we calculated what is the kind of the K effective, and then we found that the row 1, that is 1 is kind of more severe compared to what you will find at 3, 5, and 4 location. So the characteristic SAF distribution with crack length for crack tip is like row 1, and crack tip 1 is like row 3 in these cases. So then we looked at what is the most critical location from this case. So hole 1 emerges as the kind of the effective critical location, and the maximum difference is observed at 38 mm and 40 mm crack length over here. So all the analysis subsequently was restricted to hole 1 in this case. So then we looked at what is the effect of load ratio. I said that you could biaxial. Then we have this 0.25, 0.5, and 0.75. So you will notice that these are the trends for the effective SAF for this 3 conditions of variable biaxial loading. And what we can see is that the blue line shows for the load ratio 1 is the most severe case, whereas the yellow line for 0.25 is the less severe case in these cases. So as the load ratio decreases, there is a significant reduction in the SAF, and a maximum 78% was found for a crack length of 38 mm and 0.25. So then we also looked at what is the effect of crack shadowing. So for example, in this case, we have a case 1, and there could be a shadow on this crack rivets 2 and 3, or they could be on the other side of this. So these 2 were considered for the study, and what we realized is that in case of case 1, which is what is shown over here, you will notice that the case 1 has the trend, which is shown by the blue line, which has a maximum decrease in K effective at about 34 mm of the crack length. And case 2 it is minimum at some point and then later on picks up. So the effect of shadow cracks on H2, H3 on the effective SIF as the primary crack is studied, and up to 5 mm increment beyond the direct fold, and the the reduction in SIF is found to be 2.3% in reference case to the 40 mm crack length. So I'm almost done. So at crack tip 2, the whole one, the maximum reduction of SIF is about 3.16%, and case 2 is found to be more effective than case 1 in reducing SIF for both tips. So to conclude, these are the kind of salient points. I'm not going to read out all of them because I think I've already described. So I think you can read it yourself. And thank you very much. These are the references that have been used for the study. And thank you very much for the opportunity.